As we have discussed in our previous video lectures about characteristics of 1 and 2 compartment model, I just summarize. You know that drug that follows 1 compartment model stay within the bloodstream and highly perfused tissues, that is central compartment. We know central compartment, it comprises of blood and the tissues which have high blood flow such as liver, kidney, spleen, and these drugs which follow 1 compartment model has no affinity for tissues outside the compartment of central circulation. As the drug stays within the central compartment, it does not move outside the central compartment. Actually, there is no drug distribution take place. So we can say there is no rate constant for drug distribution. Mathematically, it is expressed as alpha. So there is no rate constant for drug distribution because there is no distribution, actual distribution taking place. As soon as the drug enters the central compartment, the process of elimination begins. Whereas in case of 2 compartment model, the drug has affinity for peripheral compartment. Now what are peripheral compartment? The peripheral compartment is a compartment. It comprises of the tissues which are outside the central compartment, that is peripheral compartment. It comprises of tissues with, we can say, with low blood flow or low perfused tissues such as adipose tissues, muscles. So when your drug moves from the central to peripheral and from peripheral to central, these kind of drugs, they confer to 2 compartment model. So in case of 2 compartment model, as drug actually distributing between central and peripheral compartment, as the drug moves from the central to peripheral compartment and from peripheral to central compartment, so we can say actual distribution is taking place. Since actual distribution is taking place, so in case of 2 compartment model, there are 2 rate constant. So distribution constant and elimination rate constant. Whereas in case of 1 compartment model, because the drug stays within the bloodstream and highly perfused tissue, that is central compartment, there is no distribution rate constant. But in 2 compartment model, as the actual distribution taking place between the central and the peripheral compartment, we have 2 rate constant, that is distribution rate constant and elimination rate constant. So in today's lecture, we are going to discuss about the 2 compartment model. Basically, we will be talking about the alpha distribution constant, how to determine alpha, what are the procedure, what is the technique to calculate the value of alpha, that is the distribution rate constant. In this graph on the screen, you can see the graph. You can see this is the PK profile of 2 compartment model. You can see IV bolus. So in this graph, you can see bi-exponential curve. Why it is bi-exponential? Because there are 2 exponents. One is distribution phase, another one is elimination phase. The first curve, you can see it is rapid declining phase, and the second one is elimination phase. Elimination phase is a slow declining slope, or we can say slow declining phase. Now we will learn how to calculate alpha, that is first order distribution phase. You see the graph, the second graph. Here equation is given. The equation of 2 compartment model is C is equal to AE minus alpha t plus BE minus beta t. Now what is the significance of this equation? This equation, with the help of this equation, this is mathematical model for 2 compartment model drugs following 2 compartment. So here we can find out the concentration of drug in the plasma at any time t for the drugs which follow 2 compartment model and which are administered through IV bolus route. So in this equation, we can see the parameters A, E minus alpha t plus BE minus beta t, where the first exponent AE minus alpha t, this is known as the distribution exponent, and plus second part of the equation BE minus beta T. This is the elimination constant or elimination exponent of the equation, where alpha is the distribution rate constant and beta, that is elimination rate constants. Beta tell us about the overall elimination rate constant of the drug in the body, and capital A and capital B, you can see these are known as hybrid constants or hybrid coefficients, and these are very complex parameters, and they tell us about the concentration of drug in the body immediately after administration of IV bolus in the body. And this A and B, which are hybrid coefficients, they have unit of concentration. Now we'll move ahead, we'll see the procedure. Now we will understand the procedure to calculate alpha. So there are various steps. So we'll go stepwise. Let us see what is step 1. You can see on the screen step A. What is step A? Step A, the first step is that you have to plot the plasma concentration time data. And you have to use the semi-log graph paper, and on that semi-log graph paper, what you are going to do, you administer the injection to the patient, and at various time intervals you withdraw the blood samples. You measure the plasma concentration using any sophisticated instrument like HPLC you can use. So you have to generate the data. You have to generate the data, that is time versus drug concentration data. So what has been shown on the screen is plasma concentration time data, which is plotted on the semi-log plot. So you can see the bi-exponent curve. X-axis you can see time, and y-axis you can see plasma concentrations. In the curve, when you see the curve, this bi-exponent curve, you can see the second curve is linear. The terminal portion of the second curve is linear, and you can find out the slope from this linear portion of the second curve, the terminal portion of the second curve. You can find out the slope, and the slope will give you the value of beta. So the equation is slope is equal to minus beta divided by 2.303. So the second phase of the curve, it is known as beta phase. As we have seen in this you can see in the curve, you can see the graph by exponent curve. The first phase is distribution phase, the second phase is elimination phase. So we find out the value of beta, that is elimination rate constant, from the elimination phase. Beta can be directly determined from the graph. Simply find out the slope, determine the slope of the linear portion, and that slopes give you the value of beta. So slope is equal to beta divided by 2.303. Now what is beta T half? That is elimination half-life. Beta T half is time required for any concentration on the line to decrease by 50%. So mathematically beta is equal to 0.693 divided by T half. Now let us move to the step 2. In step 2, you again see the graph by exponent curve. You can see the terminal portion of the curve. The terminal portion of the second part of the curve, that is elimination phase, is linear. So you extrapolate the linear portion of the elimination phase and you touch it with the y-axis. Now the linear elimination phase is also known as beta phase. You first of all you identify the beta phase, and then line is back extrapolated to the y-axis as shown in the graph. You can see the graph on the screen, and this straight extrapolated dotted line, you can see the dotted line. This dotted line is corresponding to the second part of the equation. We can see on the graph, see this is the equation, C is equal to E minus alpha t plus BE minus beta t. So the second part of this equation, that is BE minus beta t, this is represented by the extrapolated line in the step 2. You can see dotted lines. This dotted line, it represents or it corresponds to the second term of the bio-exponential equation, that is the elimination phase, BE minus beta t. So beta, you can find out, beta is a slope. You can find out the value of beta from the slope of the terminal linear portion of the second phase by applying the formula minus beta is divided by 2.303. Now let us move to the step 3. That is the hybrid rate constant beta, that is elimination rate constant, is determined from the slope of the line representing the beta phase. Already we have discussed this. So beta you can find out from the slope of line representing the beta phase, that is dotted line. So you have to see the terminal portion of this line. From there you can find out the value of beta. Now from how to calculate alpha. For calculating the alpha, that is distribution constant, we need to use the method of residual. Alpha, which is distribution constant, it cannot be calculated directly from the graph, but we have to use some mathematical technique that is known as method of residual. Resolution in pharmacokinetics, it means when we subtract one concentration, that is one concentration from another plasma concentration. So you have to subtract one plasma concentration data from the another plasma concentration data, and the outcome of that data is residual concentrations. So let us see the graph. You can see the graph. There is dotted line and solid line. You can see the dotted line and the solid line. The solid line or the solid curve by exponent curve, it is original curve, and the extrapolated lines are the elimination line. So the residuals are calculated from the difference between the original plasma concentration time data and the corresponding value on the extrapolated elimination phase. So you have to subtract the plasma concentration, which is extrapolated concentrations. Dotted line, you can see the data points on the dotted line, and some data points are there on the solid lines. So you have to subtract the extrapolated concentrations from the original plasma concentration. After subtractions, when you subtract one value from another value, you get the third value. So similarly, when you subtract the one plasma concentration, or when you subtract the extrapolated concentrations from the original plasma concentrations, you get some different concentrations, and those concentrations are known as residual concentration. So what are residual concentration? When you subtract the extrapolated concentrations from the original plasma concentration, the resultant concentrations, they are known as residual concentrations. So in step 5, we are going to plot the residual concentration versus time. So now after subtracting the extrapolated concentration from the original concentration, you got the residual concentrations. Now you have to plot the data. Again, you have to use the semi-log plot. X-axis you take the time data, and y-axis you take the residual concentrations. These residual concentrations you have obtained after subtracting the extrapolated concentration from the original concentration. So when you plot a graph between the residual concentrations which you have plotted on the y-axis and the time data points which you have plotted on the x-axis, and you have used the semi-log plot, you get the straight line. So whenever you plot the time data versus residual concentration data, you get a straight line, and the slope of the straight line gives you the value of alpha. So here the slope is equal to alpha divided by 2.303. So this line, which is the residual line, it represents the first part of the equation, by exponential equation, that is C is equal to AE minus alpha t plus BE minus beta t. So the first part of the by exponential equation, that is AE minus alpha t, it is represented by this residual line. So these residual are plotted versus their corresponding time. The residual versus time plot is linear on the semi-log scale, and corresponding to this is correspond to term AE minus alpha t in the bio-exponential equation. The hybrid rate constant alpha is determined from the slope of the line. Mathematically, slope is equal to minus alpha divided by 2.303. Now we are going to find the distribution half-life, that is alpha T half. So what is mathematically distribution T half? That is 0.693 divided by alpha. So this is the method which is known as method residual, with the help of which we can find out or we can calculate the value of alpha. Now when we talk about the two compartment model, there are four important parameters. If I ask you what are the pK parameters of two compartment models, so your answer would be A, B, alpha and beta. So beta is overall elimination rate constant, alpha is distribution rate constant. So how would you determine beta? Beta can be directly obtained from the graph, whereas for alpha we need to use the method of residual. Now this is the schematic diagram of the two compartment model. You can see two compartment, the peripheral compartment and the central compartment. So your drug is moving from central to peripheral, and you can see one parameter K12. What is this K12? And you can also see K21. Then what is this K21? Now K12 is the first order transfer rate from the central compartment to the peripheral compartment, and the unit is time inverse. What is K21? K21 is the first order elimination rate constant from the central, K21 is the movement of drug or transfer rate constant of a drug from peripheral to central compartment. X is the amount of drug. This is also a parameter. What is X? X is the amount of drug in the central compartment. It has the unit of mass. What is Y? The amount of drug in the peripheral compartment. It has unit of mass. Now there is one more term, VC. VC is the volume of central compartment. Now these are the parameters. So now we'll see the formulas, how to calculate into compartment models. AUC, area under curve. So what is the formula to calculate AUC? Area under curve from 0 to infinity in case of two compartment. So AUC 0 to infinity is equal to A divided by alpha plus B divided by beta. From you just find how to, so you find out the value of A, B, alpha and beta, you substitute the values and you can find out the value of AUC. From where you will get the value of beta? Directly from the linear portion of the elimination line. Alpha you can get it from the method of residual. A and B, which are the hybrid coefficients, and the unit is concentration. These you can directly get from the graph or pK profile of two compartment model IV bolus. Now to calculate A, the formula is, you can see on the screen, A is equal to D bracket, open the bracket, alpha minus K21, close the bracket, divided by VC. VC is the central, it is a compartment, central compartment, volume of distribution of central compartment, then alpha minus beta. So K21 and VCD, if you have the values of these parameters, you can easily find out the value of A. What is D here? D is the amount dose. Now similarly you can find out the value of B. B is equal to, what is the formula of B? B is a hybrid coefficient, so the formula of B is D divided D, open the bracket, K21 minus beta divided by VC into alpha minus beta. Now clearance, it is also very important pharmacokinetic parameter. We have already discussed in the previous videos what is clearance in detail. In case of two compartment, again the total clearance can be calculated using the formula dose divided by AUC 0 to infinity. So how would you find out the value of K21, that is transfer rate constant from the peripheral to central compartment, K21, which is equal to alpha into beta divided by K3. Then how to find the value of K12, that is transfer rate constant from the central to peripheral compartment, K12 is equal to alpha plus beta minus K21 plus K3. Now what is the formula of K3? So K3 is equal to clearance, total clearance divided by volume of distribution of central compartment. So today we have discussed about the method to calculate alpha And we also saw some mathematical formulas, very important formulas related to two-compartment model. So I thank you all for your patience listening. Thank you.